All right. Oh, there we go. So, mechanisms. Up until this point, we've now learned two ways to find the order of reaction to write the rate law. We can do it through method of initial rates. We can do it through integrated rate law, running the time and the concentration, figuring out from your calculator or graphical analysis what order of reaction we have, and therefore what the rate law is. A third way is through the proposed mechanism of the reaction. So let me talk a little bit about what mechanisms are. This reaction here, H2O2 plus 2I minus plus 2H plus goes to I2 plus 2H2O. Some reactions, like this one, occur in multiple steps. Actually, a lot of reactions occur in multiple steps. Okay? So we have this proposed mechanism. At no point are you going to be writing out mechanisms. That's beyond the scope of what you need to know for this course. Okay? But first what happens is one of the H2O2 molecule reacts with one of the I minus molecules. So that's my first step. And that forms this compound HOI plus OH minus. And then that HOI that formed in the first step collides with the other I minus molecule, or ion, forming I2 and OH minus. And then in the third step, those two hydroxide ions that were produced in the first two steps react with the two hydrogen ions that are in the reaction flask, forming two water molecules. Okay? So this is a three-step mechanism. This will add up to the overall equation, to the overall reaction. So this is the overall reaction that's occurring, but it's occurring in three steps. One of the steps of a mechanism will always be identified as being the slow step. There will always be one step that's slower than the others. Okay? In this case, my first step is the slow step. But we don't know, we aren't given information on like how much slower. It could be just a smidge slower than the other two. But it's still slower. Okay? The slow step is also called the rate determining step. Okay, and I'll talk more about that in just a little bit. Let's first just talk about these intermediates and catalysts. Okay? An intermediate is a substance that is produced in an early step and then used in a later step. A catalyst is a substance that is used in an early step and then produced back later. Okay, so an intermediate is a product first and then it becomes a reactant. A catalyst is a reactant first and then it becomes a product. Okay? So used, then produced. Intermediates and catalysts are not part of the overall equation. Okay? Because what ends up happening is they cancel out. So it's kind of like with Hess's law, what we did with the last unit, only you don't actually have to manipulate any of the mechanisms. Another way to think about it, it's kind of like when we were balancing redox. Once you had your multiple things and you add them up, you canceled things that were the same on both sides. Okay? Or like when we were doing net ionic equations. Things that were spectator ions, they were the same on both sides, they weren't in the overall equation. Okay? So, do we have any intermediates in this reaction? OH minus, because it's produced in the first two steps and then used in the third step. So OH minus is an intermediate. And HOI, because it's produced in the first one, used in the second one. Okay? Both of those things are not in the overall equation. So it's another hint that, hey, we've identified our intermediates correctly. Does this reaction have any catalysts? Nope. No catalyst for this one. But a catalyst would be one where if it was a reactant at first and then we get it back out at the end. Okay? All right, so our energy profile for this three-step mechanism, we've drawn energy profiles before. they look kind of like this, where you have energy and time, and you've probably seen things like this before, right? Now this is showing for the overall reaction, and there's the activation energy. When we have mechanism, a multi-step mechanism, that's what I want to erase that. You're going to have a peak for every step. Okay, so how many peaks are we going to have? 3. And the reason the slow step is because that requires the most amount of energy for it to occur. That's what causes it to be the slow step. So which peak is going to be the highest? The first peak. So for your energy profile, time is always on the x-axis, and energy is on the y. And we're going to have 3 peaks. The first one just needs to be higher than the other 2. We don't have any other data than that. We don't know the relative heights of the 2 fast steps, their peaks. We don't know if one is going to be higher than the other. Probably, because they're not the exact same thing. But we don't know. Okay? But as long as your first peak is the highest, I don't care what your other ones look like. As long as they're lower, as long as you have 3 peaks, and the first one's the highest. Okay? And that's what we're going to label as the rate determining step, or the RDS. Okay. The rate determining step, the slow step, will not always be the first step. It's just in this one it is. So just be aware that your large peak might not always be first. It will either give you which one is slow, or it'll give you enough information to figure that out. Okay? So from that, we can figure out the rate law. Because which step is going to help us determine our rate law? The rate determining step. That's why it's called the rate determining step. So from the slow step, we're going to write our rate law. This is the one place where you're going to use the coefficients from the equation. Back in method of initial rates and integrated rate law, the orders did not necessarily correspond to the coefficients from the balanced chemical equation. Here it does, because you're using the coefficients of just the slow step. Okay? So my rate law is going to be rate equals K times H2O2. What coefficient does H2O2 have? In that first step, 1. And then I minus, what coefficient does I minus have in the first step? 1. Okay, so it's first order, H2O2, first order, I minus. And the reason why is because those are the coefficients from the slow step. Okay. So if you're given a mechanism and you're told which one's the slow step, you're probably going to be writing the rate law from that. Sometimes you might be given a mechanism and you're not told which one's the slow step, but you're told the rate law. And then from the rate law, you have to figure out, oh, which one was probably the slow step in the mechanism. Okay, so you can work either direction. Okay. We have one more thing we're going to do with this problem. What if the second step was our slow step? What would the rate law look like? What would our rate law look like? Well, rate equals K times HOI to the first times. When we do next unit, what is it, 5, we'll actually see where this is not 100% correct. Because when you have an intermediate, you can't actually have it in the rate law because you cannot actually impact its amount. But we need to learn a little bit about equilibrium before we can do that. So don't worry. Okay? But for right now, this is what we would say would be the rate law. Okay? You guys want to try the next one? Like, this should be really easy for you. This should be super simple. Okay? It's probably the easiest way to find the rate law. All right, so let's go ahead and look at this one. going to pause the video while you guys take a moment to go through them. You can work together, help each other. So you're going to add up all the reactions, all the steps in the mechanism to get to the overall equation. What did you get as our overall reaction? Good. All right. Which substances, or which species, were intermediates? HOOBR, because it was produced in the third step and then immediately used in the fourth step. So you canceled it out when you were adding up to get to the overall equation, right? Did we have any catalysts? Yes, what? HOBR, because we used it in the first two steps and then we got them back out in the last step. Okay, so they canceled out as well. And everything else, you know, wasn't the same on both sides, so it doesn't cancel out. Cool? All right. How many peaks is our diagram going to have? 4. 4 peaks. So what's on my x-axis? Time. I'm going to make this a little bit longer. What's on my y? Yep, which stands for energy. You said 4 peaks. Which one's going to be the largest? The third one. Does it matter the relative heights of the other peaks? Nope. Did you notice that the first 2 steps in my mechanism were the same? So probably my first 2 peaks are going to be the same height. Most likely. Okay? So like 1, 2, and then woo, really obvious. And then maybe this one was like kind of halfway. Okay, or whatever. Okay? But really obvious that that's my rate determining step. And what's my rate law? Cool? All right, so now you have the knowledge. Shh. Now you have the knowledge to be able to do homework 4B, which you got last class, but I said that we would be learning that stuff this class. I just had it already printed for you. Okay?